Even though air travel today is safer, less expensive, and faster than ever, many people still have complaints. One of the most often heard criticisms related to air travel is about delayed or canceled flights. Logically, it makes sense that a country as large as ours, with more than 7,000 flights per hour, would experience some delays or cancellations. But it is not always easy to be forgiving and logical when you are the one sitting at the gate or on the tarmac hoping to get to your destination. So how can changes be made to make air travel even more reliably on time? NASA and its partners are pushing to make present and future travel more reliable with less delays and cancellations by improving our already robust systems. NASA, the FAA, airlines, industry, and academia have all been working on a collection of Airspace Technology Demonstrations, or ATDs, that are geared toward delivering near and long-term benefits that will help improve our air transportation system. Coming up on this episode of NASA X, we will look at two of these ATDs and find out how this incredibly complex work is being developed from off the drawing board into the state-of-the-art for air traffic management. We will see how the first test, ATD-1, will investigate ways to improve scheduling, merging, and spacing capabilities, as well as increasing fuel efficiency, while ATD-2 will develop and adjust precision schedules for gates, spots, runways, arrival and departures. And we will see how these ATDs are being used to develop innovative new technologies and procedures to make our already world-class system even better. For anyone who travels, we have all been here. Stuck on a flight, circling the airport, waiting for our turn to land, or stuck on the ground, waiting for our connecting flight to finally arrive. It seems like being delayed at airports has become the norm, and with more and more people traveling by air every year, if something isn't done, then this problem will only get worse. Luckily for all of us, NASA and their commercial partners have developed a new technology called Flight Deck Interval Management, or FIM, to minimize these types of delays and to make travel faster and more economical for all of us. Much of the early testing and research for this new approach was performed by using sophisticated computers and flight simulators at NASA field centers. But to make sure this system will work for commercial flights, NASA must now test this tech in real-world conditions, on real flight tests. So NASA and its partners are here in Seattle, Washington, taking part in a comprehensive flight test campaign called ATD-1, or Air Traffic Management Technology Demonstration 1. Once they're done here, they hope to be one step closer to minimizing those annoying delays. To understand what the ATD-1 program is and how they hope to integrate the Flight Deck Interval Management System into commercial aircraft, we must first understand why there are flight delays today. Currently, the system works like this. Air traffic controllers are in charge of the spacing and sequencing of all inbound aircraft. The air traffic controllers use radar to track and manage all incoming aircraft, giving speed up, slow down, and vector commands to the pilots coming into land. The pilots comply with these commands and, based on those instructions, are placed in a landing queue in front of or behind other aircraft. Although our current air traffic management system and radar technology does a good job of managing all those flights, this is where delays begin. Radar can be imprecise, and because voice communication between humans introduces delays, the air traffic controllers are cautious and require greater spacing between airplanes to maintain safety. The spacing gets even larger at peak times and in bad weather, causing more delays. Because researchers know why there are delays, they think they know how to solve the problem.
With the current technology that we use, which a lot of it from the radar dates from the 40s and 50s, with a lot of the procedures that we've built around it from the 60s, 70s, and 80s, that we're pretty close to the maximum capacity that we have with the current system. So this does specifically address that we think we've hit that limit, and we're looking for a new way to do business so that it is more scalable, more responsive, more efficient. And so instead of relying just on radar, which is still very effective, we're relying on something called ADS-B, which is automatic dependent surveillance, which is broadcasted. And so now we have the aircraft are actually sending out signals that all the other aircraft and the ground can see. This gives us much more accurate information. We can create more sophisticated plans, and then the decision support tools that AIM's built for the controllers and what we're building for the pilot allow the controllers and pilots both to execute to this much more sophisticated schedule than we have currently.
With this new technology, the pilots will no longer be reliant only on air traffic control, but can follow automated directions on their onboard flight deck interval management system.
Air traffic controllers are responsible for spacing. With film and understanding ADS-B, we now have the capability on the airplane that we can get signals from the other airplanes and know where they're at. We know their state data, we know their speeds, their altitudes, and so we can actually space them off of each other so that we are getting more airplanes through. Right now, air traffic controllers space people further apart because they don't know necessarily the winds and how the airplane is reacting, because every airplane reacts differently. But if you put that information in the cockpit with the pilot and have the air traffic controller issue him a flight deck interval management, a film clearance, then he can space off the guy in front of him, so you're getting more airplanes through. It's not an easy problem to solve, because right now you've got everybody lined up, but what about when you have those guys coming from the other direction? You've got to create a space for them and slide them into the chain to get them in also. And so it'll be boom, boom, boom. Even when you get weather, you will be able to target them in and get more airplanes in and out so that you're increasing your throughput, which saves fuel, saves time, saves money ultimately for the consumer.
It works like this. This NASA-developed software keeps track of the speed and position of the airplanes as they approach an airport. GPS signals determine each plane's location and ground speed, then broadcasts this information to satellites and ground stations about once every second. The FIM system automatically calculates how fast the planes should be traveling to maintain the proper spacing between them, and displays that information on a tablet in the plane's cockpits. The pilots see their speed and the speed of other aircraft around them in real time, allowing for safe distancing until the landing gear touches the ground. Because this software can predict the moment when an airplane touches down within a few seconds, pilots and ground controllers plot each plane's route more easily and efficiently. With tighter spacing, planes won't loiter in the air as long, which means there is the potential to use less fuel, reduce noise and pollution for communities around airports, and have fewer flight delays for the flying public. Working with Boeing, Honeywell, the FAA, United Airlines, and others, this NASA-led project performed the flight tests out of Boeing Field and out of SeaTac Airport in Seattle. For these tests, they flew 3 research vehicles, including Honeywell 757, a Honeywell business jet, and a United Airlines 737. The planes, each carrying the necessary tech, ran simulated approaches and landings at a Grant County International Airport near Moses Lake, which is about 120 miles east of Seattle. These tests were invaluable, helping the team to see what works and what needs some tweaking.
The average day will probably start off 7 o'clock, 7:30. We'll have a mass brief where we get all the flight crews and the flight test directors and engineers together. We'll talk about the day. We're going to have air traffic control representatives in the briefing with us as well. And then by 9 o'clock, 9:30, we will be at the aircraft and take off from both Boeing Field, which is where the 2 Honeywell aircraft will be, and then Seattle Tacoma International, which is where the United aircraft will be.
As the day begins, each plane takes off and they head to their testing area. Then, Follow the Leader begins.
It's interesting that you say follow the leader, because that's a very simple description of what we're trying to do. There's one aircraft that would be identified as a lead aircraft. They're using automatic dependent surveillance broadcast signals. The aircraft that are following them have been given instructions: follow your leader, follow that aircraft by 180 seconds. And now what we've developed are software tools and displays that can show the flight crews whether they're at that 180 seconds, whether they're going a little bit too quickly or a little bit too slow. If they're a little bit out of position, it can guide them back into that position with these tools. And everybody stays in line, and the flow of traffic continues on down to the runway very smoothly that way.
So far, this software-based technology is being well received by industry and NASA. In fact, the Terminal Sequencing and Spacing, or TSAS, software that is part of this project won NASA's 2017 Software of the Year award for its importance to flight operations. What TSAS does is to determine where each aircraft should be to maintain their fuel-efficient, continuous descent approach and indicate to controllers what speed that aircraft should fly. Controllers see the calculated speed on a computer screen and then pass appropriate directions to speed up, slow down, or maintain current speed along to the aircraft. The goal is to use this kind of speed control to enable all of the continuously descending aircraft to safely merge together at a point in the sky where they can be handed off to an airport for their final approach and clearance to land. All of the tools in ATD-1 testing are helping to lead the way to more efficiency in the air traffic system, making travel more reliable and consistent. More testing will continue in the months to come, but as for right now, this approach looks incredibly promising. The ATD-1 test was an important step in helping us understand the technology needed to help align aircraft traffic for the just prior to top of descent spacing all the way down to the runway. But that is just one part of the problem. Other areas, including the arrival, departure, and surface areas around the airport, will also need to be updated and modernized to complete the overhaul. This is a very challenging endeavor due to the fact that we can't just change out the current system overnight. We must work in incremental steps to learn how to improve this system too. Even though our air traffic control system is so reliable, there's been a push in recent years to innovate and update it to help it perform even better. Although a layperson might think that these proposed changes would come from industry or from the FAA, in truth, NASA has always played a key role in driving changes that maintain safety and improve efficiency in air transportation. The agency best equipped to make these changes is NASA. Daily operations, safety, regulations, and policy for our air traffic system are run by the FAA. Because just keeping the system running is such a daunting task, the FAA focuses almost exclusively on near-term activities and goals. The airlines are in business to fly passengers in a very competitive market, so long-term research on their own is not feasible either. But NASA has the ability to take the long view and to lead transformative research efforts that could take years. Together, NASA, the FAA, air traffic controllers, and industry can develop a plan of action that meets everyone's needs, including those of the flying public.
What the FAA does is it tries to manage the flow of aircraft through the airspace so the carriers, the Uniteds, the Americans can provide you the opportunity to fly from where you live to where you want to go. The FAA tries to do that in the most cost-effective and efficient way, so because there's demand grows, we need to try to keep that a cost-effective solution and a reasonable solution for you as a passenger. The last thing you want to do is spend hours in airports waiting for your next flight. What NASA does is build the technologies that allow us to meet that need. So they provide tools that help us move aircraft efficiently into airports, through airports, and out of airports. And we're really grateful for that work. So the tools they build help make the flights more fuel efficient, more on time, which reduces the cost for the airlines, which should keep your ticket prices down and make it an easy, enjoyable visit to wherever you want to go.
Although our air transportation system is the best in the world, there are still inefficiencies. In a busy airport environment, a lack of communication and coordination can be issues amongst the operators who are responsible for managing the phases of flights. And with the growth of air traffic, terminal airspace is becoming even more congested and inefficient, which can lead to bottlenecks on the surface. So how can we find ways to make the current system more efficient? This is where NASA's ATD-2 demonstration comes in. The ATD-2 testing focuses on ways to integrate the different systems that can cause these inefficiencies into a new, innovative system. It will integrate arrival, departure, and surface technologies, or IADS, and other older technologies to improve the traffic management system at the airport. This will increase predictability of aircraft movement times, improve overall system efficiency, and reduce fuel burn and emissions. That means that this tool will help airlines save money and passengers save time with less delays. In order to learn how to implement this system nationwide, NASA and its partners are testing the new systems in a real-world environment. Air traffic controllers and airline personnel will evaluate the system as they use it to manage air traffic operations at a busy hub airport.
I've been involved with NASA since about 1995 and been participating in a lot of their demonstrations. I knew they were the right people to go to, and we got together and we talked it through.
After looking at several options, Charlotte Douglas International Airport in Charlotte, North Carolina, was chosen to conduct initial testing. Charlotte was ideal for many reasons.
It turned out when the FAA and NASA were looking for a location to demo this technology they were developing, Charlotte turned out to be an ideal location, primarily because of where we're located along the East Coast and the multiple centers that we deal with. We have a very difficult time getting aircraft off the Charlotte airport into the overhead streams, and we have 9 very definite arrival and departure banks a day at Charlotte with about 45 minutes of recovery time between each of them. You could not have tested a technology such as this at an airport like Newark, LaGuardia, or JFK. You run the risk of grinding the whole system to a halt. So Charlotte was an ideal location to roll this out, and eventually this technology, after it's incorporated into TFDM, will be rolled out to all those other busy airports. Anybody who takes a look at the Charlotte Douglas International Airport and sees a map of it sees the runways of a major international airport. If they look closely, however, they'll see that we have the ramp space of a mid-sized regional airport. And our departure and arrival banks at Charlotte pretty much overlap 9 times a day, and we move between 75 to 80 arrivals and 75 to 80 departures through a very small confined ramp space at Charlotte. We can't build our way out of this one. To find the inefficiencies that are there and to make things more efficient, we're going to have to use technology. And once we begin using this technology and are sharing the information that we have, and the airlines are sharing the information they have with us, we should both be able to come to a much better solution to this problem and become more efficient.
The partnership between American Airlines, the Charlotte Airport, NASA, the FAA, both headquarters and locally with our controllers, is exceptional here. And we've worked very, very well as a team to achieve the objectives that we wanted from the project. And I think it's been a huge success because of that collaboration.
We're very excited about this partnership in Charlotte especially, and we have not only American Airlines involved with NASA, but the local FAA folks are involved, the airport authorities involved. It's a real true collaboration. The airport surface for many, many years has been sort of the black hole in terms of understanding what's happening on the surface and how that connects to the overhead stream of aircraft. So what we want to do is be able to give the traveling public, whether it's American Airlines or other carriers, a more predictable experience, because there's still a lot of uncertainty today when you push away from the gate and you wait to take off, and I think we've all been through that at one time or the other.
The ATD-2 software will combine multiple concepts and technologies, including the FAA's 3 major operational decision support system technologies called Traffic Flow Management System, Time-Based Flow Management, and Terminal Flight Data Manager.
Some of the most powerful stuff, it's the under-the-hood stuff that NASA has done with this dashboard that gives us a very quick look of how the health of the airport is going. We measure throughput in the FAA by number of arrivals and departures at the airport. And what we're trying to do is find the inefficiencies that are there and optimize the throughput by putting aircraft in the best possible place to meet their slot in the overhead stream. We have very high hopes that we can make things more efficient, and we'll be using this equipment to do that.
Another big technology change is just the exchange of information amongst the different players in the system. Right now, each of the entities, the facilities that are responsible for controlling the traffic pretty much operate within their sphere of influence without a lot of information flowing between the facilities. And so a big part of ATD2 is to help that communications flow amongst the different people that all are responsible for solving part of the problem. Our objective is to improve the predictability of these integrated arrival departure surface operations, because a lot of the inefficiencies that are inherent in today's system are due to the lack of predictability. People do not know what to expect when they're managing the traffic, both on the FAA side and the air carrier side. And so they're conservative in their approach. They introduce larger buffers and greater than needed traffic management constraints because they don't know what's going to happen. But by sharing information amongst the parties that are trying to solve the problem and tying it all together with a time-based scheduling system, we expect to improve the predictability and help folks be less conservative in their approach to managing the traffic, to provide smaller buffers in the system.
It's a lot of different systems that may be out there today operating separately, but if we can connect them through networking, have the information and data flowing between the systems. But it's not just the fact that the data and information is beginning to flow across networks or into the other systems. It's what you do with that data also. So a lot of our technologies, you could think of, the kids today might think of as apps. So these are applications that the operators can use, but it's telling them very important and unique information about the schedule, what aircraft should be in position at what time in order for the overall operation to work most efficiently. And that information will be shared with all the participants, whereas now only part of the information is usually resident with each of the participants. But with that picture that everybody has, everybody knows what we're working towards, it can function a lot more efficiently.
This increased predictability and merging of technologies has the potential for huge benefits. Initial projections of 10 congested airports show the potential for ATD2's departure scheduling to substantially reduce overall departure delay by 40% and enable flights to absorb their delays at the gate, which leads to more environmentally friendly operations. Over a 20-year life cycle, conservative estimates indicate a potential savings of $8.2 billion.
I have been in the airline industry a long time, and I can say over the last 15 or 20 years I've been involved with several different projects, if you will, and partnerships with NASA. They've all yielded very good results. I think this is sort of the most exciting of all because it brings a lot more of the pieces together in connecting the airport itself with the airspace around the airport and overhead.
I have seen more benefit from this program than probably any other thing I've worked on in my 36 years as an air traffic controller.
It is clear that change is coming to our national airspace, and fortunately, NASA, the FAA, air traffic controllers, and their industry partners are all working together to make sure that these changes are not only seamless, but improve our quality of life and the overall transportation system. Although you may not see the inner workings of this unique system, the increased predictability will undoubtedly make flying less uncertain and much more enjoyable.